What's up, everyone? It's Precalc time with Miss Wesley. Very happy to be here. The examples we tried today, if you want to follow along, you can find them on page 16 of your Polar packet where the heading says powers is what we'll talk about today, and roots of complex numbers. And I got a question for you. Don't you love it when you see something that would have taken you a whole lot of time to complete and you find a shortcut for that method? Well, today's lesson is going to be for you, so get excited. As I scroll to the middle of the page here where it says powers of complex numbers, here's where we'll start. You'll see kind of a grimacing mathematician. That is none other than French mathematician Abraham de Moivre, who lived in the 16 and 1700s. You can thank him for the theories of recurring series and partial fractions, which I seem to recall we didn't mind working with too much. And we'll look at this in a second. The joke for the day is, my wife asked me to pass her some lipstick and I handed her a glue stick. She hasn't talked to me since. Consider, I want to build off of what we had been doing in the previous lesson where we multiplied. We used shortcuts for multiplying and dividing complex numbers in polar form. We can actually take that multiplication shortcut here and work ourselves to a formula or to a shortcut for taking powers of complex numbers in polar form. So if you have like an r cis theta up here, z is r cis theta, z squared, well, you'd be multiplying the two r's. So we know from our rule it's r times r. Your new modulus is r squared. Then it's cosine plus I sine, so I'll just write it in our shorthand, cis. You would add the two arguments, add the theta, so theta plus theta gives you 2 theta. Seems kind of nice and concise, and I'm almost noticing a pattern. So for first power is r cis theta, second power of that complex number is r squared cis 2 theta. I wonder about the third power. Well, you take what you just put, so z squared was r squared cosine plus I sine 2 theta, and your goal is to multiply it by another r cis theta, right? You want the third power. Well, shouldn't the pattern continue? You'll get r squared times r, so r to the third, cosine plus I sine, and then 2 theta plus another theta, so you get 3 theta. And then I hope the pattern's becoming pretty obvious. This is just building off of that multiplication rule we had the other day. So this will be z to the fourth would be r to the fourth, raise the r to that power, and then cis, don't raise theta to that power, multiply, right? Theta by the number of that power. And same thing should work to the fifth and so on, r to the fifth, cosine plus I sine 5 theta. I'll just put a dot, dot, dot. And that is called de Moivre's theorem. We will actually, let's just recopy it down here in general terms. Z to the nth, so a complex number to the nth power. You'll be taking the modulus and raising it to the nth power. And then cosine plus I sine, let's write it out. Cosine of what? It'll be n theta plus I times the sine of n theta. So this will be helpful when we want to convert back to rectangular form. It's nice to write it out the full way. In shorthand, r to the nth, cis n theta. Okay? And this is all great converting practice too. I want to scroll to the next page. It says, use de Moivre's theorem to find the power of a complex number, and number 1 is set up for you already in polar form. So we should be able to just apply the theorem with no initial conversion. So theorem says, take the r, take the 2, raise it to the power. So we'll raise 2 to the 8th. And then cosine plus I sine, here's my shorthand. Let's take pi over 2, don't raise it to the 8th, multiply it by 8. So it'll be 8 times pi over 2. So we've got 2 to the 8th, 256, cosine plus I sine of 4 pi. Good polar format of that answer. Beautiful. This is also known as 256 cis. What else is coterminal to 4 pi? That's convenient. 2 pi is the same angle, as is 0. Here's your polar version of the answer. Always convert these answers to rectangular. It's good conversion practice. Plus this one, cis 0, so you're 0 degrees. We're over on the polar axis to the right, and we're 256 units out. This conversion wouldn't be bad. I think people can tell. The x would be 256, and the y would be 0. You get 256 plus 0i. So here is your answer in rectangular form, which is kind of wild. You take that polar form of the complex number, raise it to the 8th, and all you get is 256. Here is, just to be thorough about it, here's the expanded version of it. Cosine of 0 plus I sine of 0. This is going to prove that 256 is the correct answer because we know cosine of 0 is 1 And we also know the sine of 0 is 0. So this expression also simplifies to that final answer of 256. Let's take a look at number 2. Now, for the rest of the page, I wasn't so nice. I didn't give you the complex number in polar form to start out with the power on the outside. It starts in rectangular form, but I just think this is kind of cool. We've gone over shortcuts for expanding binomials with Pascal's triangle and the binomial theorem in the past. This polar shortcut for a complex number is really cool because none of us, I would hope that none of us would feel like writing out this binomial 12 times and foiling it with itself. Let's do a quick conversion to polar form. Let's find the inside of these parentheses that are raised to the 12th power in polar form. So we got to find the r and the theta. So let's find r first. We can use our same conversion rules. Keep in mind that the inside of this, not the final answer, but the inside of this has a negative x value if this is an x plus yi, and a positive y value. Right? So we're this way and then we're up. We're somewhere in quadrant 2, which will really help when we're about to calculate what theta is going to be. But how about r? R squared always equals this x squared plus y squared. So r equals the square root of 1, negative 1 squared, plus 3, the square root of 3 squared. So r is the square root of 4, which gives you 2. The inside of that, as we convert, is going to be 2. How about theta? We use tangent of theta equaling y over x to get this value. So square root of 3 over negative 1. I need to find the arctangent of negative square root of 3. Right, and remember we're in quadrant 2 where the tangent is negative. We got to think of a good reference angle. Square root of 3 over 2 is the y value when you have a pi over 3 reference angle. So let's use here theta equals 2 pi over 3, right? We want to be in quadrant 2. Okay, so now I think we're set to be able to use De Moivre's theorem to easily raise this expression to the 12th power. Let's rewrite it polarly. On the inside, we got 2 cosine plus I sine, so cis. Our theta was 2 pi over 3, we said. We want to raise that to the 12th. This is so much quicker than doing it in rectangular form. I love it. So raise 2 to the 12th. Do that first. Then cis, and De Moivre's theorem says we're going to multiply the theta by 12. So 12 times 2 pi over 3 for your new argument. So 2 to the 12th, 40, 96. Cosine plus I sine. This will be 8 pi, right? 12 over 3 is 4 times 2 pi is 8 pi, which coincidentally is coterminal to 4 pi, 2 pi, and 0, kind of like the last one. So this one ends up just being a real number answer again. It's the same as 4096 cosine plus I sine of 0 degrees, which if you converted to rectangular form would just give you 4096. You're out that far on the x-axis. Okay, we're going to save number 3. Number 3 for my liking right now is a little bit too similar to the other. So go ahead, cross it off, but save the space because we'll come back up to it. Let's go out of order here and skip down to number 4 for practice. Okay, same idea. You see it in rectangular form first. We want a shortcut for having to raise it to the 5th and FOIL it out manually. And that shortcut's going to be to convert the inside to polar form. Decide on a quadrant that you think the inside's going to be because that'll help with the angle again. So are we quadrant 2 again? You're in negative x and a positive y. So again, we're in the quadrant where tangent is going to be negative for when the theta comes into play. Let's get r first. R is going to equal the square root of x squared plus y squared. So x squared negative 1 squared is a 1. Plus y squared, a 1 coefficient squared is another 1. You get r is the square root of 2 for a modulus. Theta, we need to use the definition of tangent to get theta. Theta is going to equal the inverse tangent of y over x, so 1 over negative 1. We need to think of a good reference angle for the tangent being the number negative 1. Well, tangent is 1 when theta is pi over 4. Let's put that reference angle into quadrant 2 and say theta here on the inside equals 3 pi over 4 exactly. Okay, so a conversion to start the problem. Now we get to use the shortcuts. So we'll say this equals, let's convert the inside to polar. So we said square root of 2 cosine plus I sine, and then 3 pi over 4. We want to raise that to the 5th power. And that won't be too big of a deal when we have De Moivre's theorem to help. Raise the square root of 2 to the 5th power first. Cosine plus I sine, we need 5 times 3 pi over 4. Okay. Square root of 2 to the 5th in exact form is going to be 4 square root of 2. Cis. Over here we have 15 pi over 4. You can leave it as that, or maybe we'll recognize it better if we get something lower that's coterminal. So this is exactly 4 square root of 2 cosine plus I sine. And 15 pi over 4 minus 2 pi gives you only 7 pi over 4, which is more in my wheelhouse, where I can think about its exact values one time around the unit circle. Now, this was a good one to try. For the others, I was able to look at them and kind of decide my answer was just going to come out to be a nice, even, real number. Let's try this one written out like we would normally convert back to rectangular. So this is 4 square root of 2 cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. And then it's just up to you to convert. Or I guess just plug in the values. So this is 4 square root of 2. What's the cosine of 7 pi over 4? That should be positive square root of 2 over 2 exactly. Plus I times the sine of 7 pi over 4. I believe that one should be negative square root of 2 over 2. And our answer will be left as a complex number in rectangular form. When all said and done, you've got 2 times 2. This should be a 4 here when all this stuff gets multiplied, minus 4 times I, 2 times 2 times I. So if you were to try this problem, I call it the long way, and write this out 5 times rectangularly, FOIL it with itself, long story, a bit shorter, you're going to get this as a solution. Your final answer actually does also happen to be in quadrant 4 on this one. Okay, backtracking, last but not least. Can you cross off number 3? I had to pick one where we wouldn't have the exact values just falling in our lap. So I rewrote this problem to be 3 minus 4i, picking random numbers on the inside, and I decided to raise it, to the 8th power. Something I wouldn't want to do by hand rectangularly. So step 1, let's take the inside, the angle that's in quadrant 4 for this one, and let's convert it to polar form. So real quick, r equals square root of x squared plus y squared, so 9 plus 16. And I should have recognized this is a 3, 4, 5 dimensions of a right triangle. Theta is going to be something I need the calculator for. Theta is going to equal the inverse tangent of y over x, so negative 4/3. And I want to keep in mind that I'm in quadrant 4. I'll go to the calculator for this one, and I'm going to work in radian mode the whole way. So I'll go mode just to make sure that I'm in radian mode. Perfect. And I want to take the inverse tangent of just regular 4/3 so I get a reference angle, so positive 4/3. So the calculator gives us a 0.927 for the inverse tangent of 4/3. That means, think of the picture, you're in quadrant 4. Here's your reference angle, 2 pi minus that. Let me type that in. 2 pi minus that value should give you your quadrant 4 angle where the tangent would be negative 4/3. And that gives us 5.356. That's what I wrote here. 2 pi minus that calculator approximation gives you about theta usable for this problem is going to be 5.356. And let's go back to the original, and we'll convert to polar form. So we've got 5 as our new r, cis, and then theta is about 5.356 is what we're using to the 8th power. And we applied de Moivre's theorem. 5 to the 8th is huge. 390,625. 625. Cosine plus I sine, this thing times 8, 5.356 times 8, keep using your calculator to keep this as unrounded as possible, you get 42.847. Okay, and the best way to convert is to write this out the long way. So 390,625, cosine of that approximation, 42.847, plus I sine of that same argument, 42.847. Computer programs being a little bit laggy right now, so feel free to just pause, type this into your calculator. I would type this in separately from that. You're going to get something that's so close to some whole numbers, like a 164,833. I think I rounded that. It was like 832.999, or it could have been 833.00. But just let's go nearest whole number there. And nearest whole number for this coefficient is a negative 354,144 times I. Definitely something where the process was sped up by using polar form and that approximation. I hope you guys have an excellent day. All right, tune in next time.